The title of this paper is An Application of the PROVO Vocabulary to Building Energy Performance Simulation. The authors are Hoare, Sergio Pinheiro, and James O'Donnell. Cathal and James are part of the School of Mechanical and Materials Engineering, University College Dublin, and also part of the Energy Institute, University College Dublin. Sergio works as an employee for BAM Ireland. And I'm Cathal. I'm the lead author for the paper, and I'll also be making today's presentation. The subject matter of this presentation is an investigation of the practical application of PROVO, which is data and provenance lineage vocabulary that was created by and promulgated by W3C, or the World Wide Web Consortium. And its purpose is to record provenance about processes, and in this case, we'll examine its application to recording building energy performance simulation, or BEPS from here on, provenance. The structure of our paper is as follows. We outline our concept of provenance and its purposes. We give an overview, a general overview of the BEPS process. We give an overview of how we record provenance before introducing the PROVO vocabulary and demonstrating how we represent a BEPS process step using PROVO. And then finally, we'll show some of the provenance interfaces that front a web app that we've developed to help BEPS engineers manage provenance about their simulation processes. The area of the application of provenance is very important. And we'd like to point out that we consider provenance to be beyond the concept of change management. We want to record not only the changes that were made, but also how the changes were made, what processes influenced those changes, and who carried out those provenances. Explainability is considered as one of the more important open challenges in AI research. The area of explainable results is a developing field in artificial intelligence. Explainability extends to recreating a process accurately and by introducing small perturbations, understanding which are the most significant inputs in a process. By understanding a process to this depth, we can identify reasons, for example, for performance gaps between a simulation and reality, the reality of an operational building, or we can trace errors in the process. Furthermore, if a performance gap or an error exists in the process, we can also reason about the process to identify outputs that use those results, then redact or retract those results or otherwise correct them. We use the PROVO ontology to express this provenance information. Because it's expressed as a semantic model, we can also reason about the BEPS process. We will present how we use PROVO and also describe a web-based assistant that engineers can use to capture their BEPS process. Something that is not a key subject matter of the paper, but is part of the system and important to mention, even if only briefly, is our work to provide a mechanism that describes an engineer's ability to express confidence in the output of each step of the BEPS process. To do this, we have engineers provide an assessment of the impact of each step across dimensions, such as completeness, validity, timeliness, and consistency of data. These values are input to a weighted aggregation function. The scores evolve from step to step and then provide a final score that's associated with the output of the BEPS process to describe an engineer's confidence in that output. The BEPS process, in order to understand the BEPS process, we interviewed several engineers that develop and work in this area. We developed a generic expression of the steps involved in the process, and that's shown in the following diagram. And we can see that the steps range from data collection through the use of a BIM tool, export tools, data transformations, quality control, an import tool to Energy Plus, the use of Energy Plus, and then the ongoing use of the outputs from the simulation. The first step is data collection. Perhaps this is one of the most important steps. Ideally, we could record the details of everything from operators that carried out measurements and surveys to the tools that they used. Step 2 is the BIM tool, and perhaps the first step that's carried out in the engineering office. Here, we want to record details such as software versions, operating systems, and configuration, so that we can recreate the influence of the BIM tool on data storage. Similarly, for the export tool, we record details of settings and software versions. For transformation, quality control, and import tools, we record details of simplifications or enrichments and other processes that modify the data. How these steps are recorded is up to the enterprise. The model, rather than capture the process itself, provides a mechanism to marshal this information. The final step is also very important, and that is to essentially record, akin to citation management, for the results of the simulation process. Where are outputs used? And through knowing this, we can provide full traceability. We can identify sources that for one reason or another, we can identify outputs that for one reason or another are identified as containing errors. And we can trace back through the process to identify where the error occurred. And for example, then we can trace forward again to identify any outputs that might have similar errors. That's an example of the use of this provenance information. The overall provenance process is described in the following diagram. Inputs to the process, measurements by engineers, sensor data, etc., is input. And each of these should have a calculated quality score. Then for each of the BEPS processes, a description of the data entities, the actions carried out on those entities, and the agency of those actions is recorded. These steps result in some output, which then becomes the input to the next step. The process is repeated until a final set of results is produced. The use of these results in reports and other outputs is also recorded. Each step has a different internal structure, but because each has an input source and an output, a repetitive structure arises, and we can leverage that to describe the structure of the overall simulation process. We use the PROVO vocabulary to both manage data about the BEPS provenance, but also we can use off-the-shelf tools to then reason about the rich set of relationships captured about the provenance data. PROVO is a provenance vocabulary promulgated by the World Wide Web Consortium, or W3C. The model is made up of agents, entities, and activities. Entities are information artifacts. Activities are processes that act on entities. Agents trigger these activities and can take several forms, including humans, such as engineers, the organizations that these engineers work for, software systems. For example, we've seen BIM software or Energy Plus as a simulation tool, and tools used to make physical measurements on site. The ontology also contains a rich set of relationships between these objects. They include, for example, relationships that describe the entities that result from the execution of some activity, which agent executed an activity, etc. All of this is captured as RDF and is managed in a triple store. That's a form of database or data store that's used to manage semantic information. This information, this RDF information, can then be queried using SPARQL, a query language that admits reasoning about semantic information. Now let's look at the application of this model to one of the steps in our BEPS process. The activity we chose is export from BIM. Several agents are involved, including two software components, the BIM server and the export tool. A human agent is also involved, that is the engineer that's responsible for conducting the export, along with details of the company that they work for. Two artifacts, sensor data, which is and tool data that was input to the BEPS process and stored on the BIM server, and the export data are also recorded. A variety of relationships exist to capture the interactions between all of these objects. One key relationship is derived from which relates the two entities. This relationship relates the input to the BEPS step to its output. Given the presence of this, a query can recursively iterate from the last to the first step through the entire BEPS process. Similarly, the relationship between input and the activity and the steps output can also be used to identify a step, and from there explore relationships captured in its provenance data. To support recording information about PROVO, we developed a web application. This is intended to be a companion application for engineers so that they can readily and easily record provenance information as they move through each step of the process. We see here two screenshots. The first one gives an overview of each of the steps that was created as part of some BEPS process. Right now, 3 steps have been executed, and we can see the detail for the steps related to the third export from BIM process. We can add new steps, or we can see the detail for each of the steps. If we wanted to add a new step, this is the form that the operator would complete. The step title, the responsible agent, and an overview of and a collection of actions that relate to the task are captured. At the bottom of this screen, we can also see a form where the operator or the engineer can assess the impact of their actions on the quality of the data. That's my presentation, and I look forward to talking to you via video link to answer any of your questions. Thank you very much.